In this video, we will discuss about Doppler effect and use of Doppler effect in various types of radar.
Doppler effect is observed when either source or target is moving with some velocity or both are moving with some velocities. Suppose in this example, I have categorized this example in different cases. Suppose in case 1, the source is sending a signal with a frequency Fi to a target T, but the source is moving away from the target at some speed, suppose Vs. So in this case the target is stationary whereas the source is moving with some value. So what will be the effect of this velocity Vs on the received frequency towards the target? We know that for any signaling, for one time period, the signal will travel one wavelength, that is lambda I. So, if we consider the distance traveled by the signal in one time period when the source is moving with some velocity, we can see, suppose this is the lambda r, that is the wavelength of the received signal seen by the target, that is lambda r equal to lambda I plus delta x. If the source is not moving, that is source is stationary, then lambda x delta x will be 0. But as source is moving, so the delta x will be the velocity of the source, that is Vs, into Tp, that is the distance traveled by the source in one time period Tp with velocity Vs. So the overall wavelength will be lambda I plus Vs into Tp. This wavelength will be seen by the target. So equivalent Fr, if we calculate, it will come as Fr equal to V by V plus Vs by Fi, where V is the wave velocity of the transmitting wave and Vs is the velocity of the source object. In case 2, if the source is moving towards the stationary object, so that time the delta x will be a negative quantity, means the wavelength will be reduced from the incident wavelength. So the Fr will come as V by V minus Vs by Fi. This can be explained by a real-time example. Suppose a car is moving towards any person, then the sound wave sensed by the person, the frequency of the sound will be increased if the car is moving towards him. So like in here, the source is moving towards stationary target. So you can see this Fr is increased because the denominator quantity is less than the numerator. So similarly, if source is moving away, then the receive frequency will be less. So you can see here receive frequency is less. So similar derivation we can do for case 3 and case 4 also, where the source is stationary but the target is moving either towards the source or away from the source. So in that case this receive frequency can be derived like this. So in general, we can write down the equation as Fr equal to V plus minus Vo by V plus minus Vs into Fi. This is the general equation, and we can utilize this equation depending on different cases. We have already seen the Doppler effect and the frequency shift due to Doppler effect. We will use that phenomena in radar. How this Doppler effect is used in radar to determine the frequency, Doppler frequency, and radial velocity of the target. So you can see Fr, we have already derived Fr equal to V plus minus Vo by V into Fi, where the source is stationary but the target is moving. Normally in radar, the transmitting antenna, that is the source, will be stationary but the target will be moving. So we can derive the delta F, that is nothing but Fr minus Fi, that will come as V naught by V into Fi. In general, this V naught we can represent as Vr, where Vr stands for radial velocity. So in case of radar, as the wave will be transmitted from the source end only, and that normally the target will be the moving object. So the frequency shift at the source end will be twice the frequency shift from the target end. So in case of radar, this frequency shift will be double the frequency shift from the target. So we have seen already at the target end, if we derived this frequency shift will come as VR by V into Fi. So for radar at the source end, overall frequency shift will be due to the frequency shift of the wave that is traveled from the source plus due to the frequency shift due to the wave that is coming after reflection from the target. So this is 2 VR by V into Fi. So this V by Fi we can replace it as lambda wavelength. So frequency shift is 2 VR by lambda. This is the frequency shift, or we can call it at Doppler frequency, that is 2 Vr by lambda, where Vr is the radial velocity, relative radial velocity, and lambda is the wavelength of the transmitting wave. This same frequency shift or Doppler frequency can be derived from the phase deviation information. Suppose we know that for any wave, due to travel a distance of lambda, phase deviation will be 2 pi. So due to travel of distance 2r, that is due to if r is the distance between target source and target, so the wave will travel r plus r. Twice it will travel to after to come back to the source. So it will be 2r. So due to the traveling distance of 2r, overall phase deviation will be 2 pi by lambda into 2r. So this is 4 pi r by lambda. This is the phase deviation. So from that phase deviation information, we can derive the frequency deviation, which is nothing but 1 by 2 pi into d dt of delta phi. That is phase deviation. So we can calculate is as 2 by lambda into dr by dt. This dr by dt is nothing but the radial velocity. So again it is proved that this frequency shift or Doppler frequency is 2 into radial velocity divided by wavelength of the transmitting wave.